Hey everybody, it's MoNaCo here again.
And Mr. Milks.
We've lost track of how many videos we've done so far, but we're getting closer to the end, that is for sure. Because
I know that we're on page 26 of 27.
yes, it shouldn't matter which video number it is.
No, it really
the
isn't.
packet ain't done, you ain't done.
No, let's make them shorter and shorter so you get through them faster. How's that?
Yes. We're going to use END, the end.
The end.
No, END.
Electronegativity difference.
To determine the kind of bond present. We did
Right.
this a little bit in our preview videos of the unit,
Uh-huh.
but we're going to get into the meat and potatoes of it.
Yep.
Right?
And we did electronegativity last unit.
Right, like what it is. It's a measurement of how hard the nucleus of one atom pulls on the valence electrons of another one.
Right. How bad do I want electrons?
How thirsty you are.
That's right. Oh,
Right.
bad thirsty.
Mad thirsty son.
All right.
Electronegativity and bond formation. There's two cool periodic tables there. Color code them if you want to.
I like the one on the right a lot.
It's
really
not
neat.
only color coded, but it's three-dimensional. It shows
I really
you
like that it's
the
three-dimensional.
closer you get to the top right corner of the periodic table, the bigger, the thirstier, the stronger electronegativities these elements
Right. They're going to
have.
pull the electrons the most.
Away from other things.
Right, and now we're going to get into how to, during the bond, how do they pull on the electrons in the bond?
Because this is the true nature of chemical bonding. One atom wants electrons, the other one kind of wants it. Who's going to win the tug of war determines if it's going to be ionic, polar covalent, or non-polar covalent.
Okay.
Three different classes of bonds we're going to start talking about.
Okay, and then we're going to use these numbers from table S, subtract them, electronegativity difference. We're going to come up with some numbers here. I'm going to change some numbers here on this board for New York State standards. Okay?
Yeah, and as Mr. Milk's changing a couple of the numbers, I need you to change them in your pack too. I want you to know that in New York State, we go by these following numbers, okay? Instead of 2.0, it's 1.7. If you go and look this up independently on the internet, you might find different disparaging, which means not agreeing with us, values for what the electronegativity difference is.
Yeah. I gotta be honest with you, this is how I was always taught it. It's got to be greater than or equal to 1.7, and so then this would actually be 1.6.
Right. Right.
That's how I was always taught.
And that's fine. We also have taught the shortcuts. Non-metal, non-metal, even sharing, non-polar covalent.
There you go.
Non-metal, non-metal, uneven sharing, polar covalent.
Right.
Metal with a non-metal, straight up
Instantly
ionic.
Metal and non-metal is the fastest way to tell us at all.
So this difference in electronegativity that we're about to teach you about really helps you figure out the difference between this non-polar covalent in green there and the polar covalent in blue.
It's to further differentiate those covalent bonds. It's really what it's about.
Because those covalent bonds, being polar or non-polar, are going to play into the molecule itself being polar or non-polar.
Right. There's a nice little hint, actually, and I know this is dragging on a little bit, but here's a nice little hint. Look, the same atoms, guys, have to have the same electronegativity.
And that's pretty much all we're going to run into in our course.
If you're diatomic, you got, whether your electronegativity is 1.8 or 2.6, it's still going to be 1.8 minus 1.8, which is 0, or 2.6 minus 2.6, which is 0, because the difference.
So, for non-polar covalent bond types, we're pretty much just talking about the diatomic 7.
Pretty much.
But we'll get into non-polar covalent molecules in the next few videos. And those are actually different.
Yeah, let's stay just with bonds for right now.
Stick with the bonds for right now.
So, ionic bonds. Again, metal, non-metal, complete transfer of electrons, and then my END is going to be greater than or equal to 1.7.
And if you don't know what our ENDs are, where do you look, Mr. Milks?
Table S.
Table S. It's got all the first 89 elements that matter, and what their electronegativities are. And if I got to do difference, I must have to do subtraction. Okay. Cool. Next one, non-polar covalent bonds. So this is a non-metal and non-metal. So the top right portion of the periodic table. There's only 14 or 15 of these different elements, but they equally share the electrons. This is when we have two nonmetals that are sharing them evenly. So there is very small to no electronegativity difference. So the END there,
one isn't thirstier than the other.
Right. They have just pretty much about the same taste for the electrons, so they're going to be held and shared right smack dab in the middle. So the electronegativity difference is somewhere between 0 and 0.4. Small difference.
Super small. Right, and then to polar covalent bonds, again, are going to be two nonmetals, because it's a covalent bond. But now I'm going to have an unequal sharing of electrons.
Right.
One atom is going to be thirstier than the other one.
So one atom is going to be closer to filling its octet than the other. It's going to have a greater effective nuclear charge pulling on the electrons
Yep.
from the other atom.
Yep. And its electronegativity difference is going to end up being in between 0.5 and 1.6.
Yes. So polarity has to do with sharing of electrons.
Sure, there's a north pole and a south pole. There's like that.
That's
little bit of
magnetism.
charge.
They're opposite. Yeah.
Yeah, and it
But
ends up being a little bit of a
in
charge.
chemistry, we're talking about electrons, not magnets. Which
Well, right, but that negative, positive,
they do re-interact with magnets.
Little
You're
bit.
right. You're right.
You're
So,
right.
on a footnote,
Yeah, let's delve into this. We talked about this a little bit last year.
ion formation. Some of my Gen Chem students really understand this. I must have done it right. I don't know. So I put this into the unit to help us reaffirm the idea.
Okay.
Cation formation. Cations are positive ions.
Yes.
And only metals make these.
Basically, yes.
So on the left-hand side, we have a sodium atom,
Yep.
with
With one valence electron.
one valence electron, which is really easy for sodium to lose because it has a very low effective nuclear charge.
There you go. Boom.
So it loses that one electron real easy-like, leaving a vacant valence electron shell, and exposing underneath, which are now the ones that are on the outside, 2, 4, 6, 8 valence electrons. So sodium is actually more stable as an ion than it is as an atom,
Because it technically has a full,
valence electron shell. It's isoelectronic with a noble gas, neon.
so it's happy.
It's happiest.
Right. Now, anions can be just the opposite. Okay. A negative ion, AN ion. So it's negative. I'm going to gain an electron. I start with 7 in my valence shell.
In fluorine, yeah, I got an empty space, a gap.
Yep. And I fill it with my electron makes me happy. I have 8 is great on the outside. And I get a smidgen bit larger because my effective nuclear charge is kind of decreased. I have 9 protons now pulling on 10 electrons instead of 9.
Yeah, and those electrons are going to kind of like shift and move and spread out a little bit.
A little bit more. Yep.
Get a little elbow room because there's more of them packed in.
Yep.
So.
And we know negatives repel.
Yeah.
So there you go.
Okay, so let's see what else we got here. So here's another graphic that shows us what is going on. Metals losing electrons always form positive ions. So there you go. Lithium, the atom is big, the ion is small. Why? Because it lost a valence shell.
Yep.
There's a whole layer of the onion that ain't there anymore.
That's right.
The effective nuclear charge does increase because of reasons.
Well, there's more protons than
There's
electrons.
more protons, there's fewer shielding kernel electrons, so the effective nuclear charge increases,
Yep.
which leads us to a decrease in the radius for 2 reasons. 1, that valence shell is gone,
Lost a layer.
lost layer, and 2, the subsequent layers, the remaining layers get sucked in closer to the nucleus because there's fewer shielding
Almost
electrons.
like a double jeopardy thing.
Yeah, so the ions for metals are smaller than the atoms that form them.
There you go. All right, so nonmetals gain electrons, form negative ions, and that's the right-hand side here. Notice it's getting large. And that's because I fill my valence shell. So I have more electrons than protons, decreases my effective nuclear charge.
Right.
They can't pull quite as hard on as many electrons.
Right.
With the same number of protons. And this makes my radius increase. They need a little bit more wiggle room.
You're putting on electrons, like you're putting on weight, you get bigger.
right.
Electrons don't actually weigh anything, but they spread out in the ion, pardon me, gets bigger. So nonmetals, ions are larger than the atoms that form them.
There you go.
So, recap. END, electronegativity difference greater than or equal to 1.7 makes the compound ionic.
There you go.
What else we got to say, Mr. Mose?
Covalent is going to be now less than 1.6 in general, right? And we can break covalent into 2 places. Polar covalent is unequal sharing in between 0.5 and 1.6 electronegativity difference.
Got it.
And nonpolar covalent then is more equal sharing in between 0 and 0.4.
And the polarity of bonds and molecules is going to become something that we're going to talk about because those things, that polarity leads to other physical properties and behaviors that are important to
It
study.
does. So I'm just going to prep you guys right now that this piece was on the polarity of bonds and not molecules.
To understand the polarity of bond, then we go and start to look at the geometry of molecules.
Next video.
And then it starts to make sense. When you got a molecule, it's a certain shape with certain things in certain spots.
Need to keep them straight. They're 2
This is
very
about
different
bonds.
things.
This is about the bonds within a molecule. The molecules themselves take this into effect, but there's another layer of the onion, so to speak.
Right.
Thanks for watching.
See you guys.